All right, so picking up where we left off last time, we were talking about math that we're going to be using in this course, and specifically how the numbers that we encounter in this course, they correspond to measurements. And so we need to be good about how many digits we're displaying, because these correspond to significant figures, right? The amount of significant figures displayed corresponds to the precision of those measurements. And we got to be good about representing that carefully. So really all we did last time was learn how to take a look at a measurement and count the number of significant figures that we see. All right? We have these three rules. Non-zeros are always significant. Zeros sandwiched between non-zeros are always significant. Leading zeros, so for tiny numbers, these are never significant. And the trailing zeros, the ones at the end of a number, are only significant if that number contains a decimal. Right? So for example, 2.50 has 3 sig figs because of that decimal, but 15,000 just has 2 because there's no decimal. Cool. All right, so next skill we need to learn here. We learned how to count. Now we need to learn how to round to the correct number of sig figs. All right, so rounding to a set number of significant figures. Okay, so I'm going to put down on exam. I'm going to leave some room here for some notes. I think it's going to be helpful to just start with an example. We're going to round the following number to 3 significant figures. And I'm going to get lazy and call them sig figs. All right, so here's my number here. We have 4.123455, and we're trying to round this number here to 3 significant figures. Okay? So what we're going to do, and you're going to see me use this notation a lot throughout the course, what we're going to do is we're going to mark the last sig fig in our number. In our measurement, really, we should call it. All right, so I need to round this to 3 sig figs. So I'm going to start counting here. My first significant figure is this 4, then the 1, then the 2. So this is my third sig fig. And I'm going to mark with a bar here. That indicates what the last significant digit is in that measurement. Okay, now in order to round, we're going to look at the digit to the right. And we're going to note, we're going to look exactly 1 digit to the right. So I'm only going to look at this 3. I don't care what the rest of the number is telling me at all. Could have been, those could be any number whatsoever. Doesn't matter. The only thing that I look at when I round is that immediate next door neighbor. Okay? All right, we're going to round down is the phrase, which is a little bit of a misnomer because really means that we keep the number the same. If it's less than 5. So in this case here, I look next door at that 3. Is 3 less than 5? Yes, awesome, okay. So I'm going to round this number down. Importantly, that just means I keep that to the exact same. So this would round to 3 sig figs to 4.12. All right, if instead I had something like 4, 1, 2, 6, 4, 3, again rounding to 3 sig figs, now I'm going to look next door, and this is a 6. So since this is greater than or equal to 5, we're going to round up. right, if it's greater than or equal to 5. So what that means is I'm going to take that 2 and I'm going to round it up to a 3, 4.13. All right, the last thing I'm going to put here that's really important to keep in mind is when we're done rounding, we must display the correct number of sig figs. So if I say round to 3 sig figs, the answer that you give me at the end better have 3 sig figs on it, right? That's what it means to round to 3 sig figs. So when we're done rounding, we must display that correct number of sig figs. Now here I'm arbitrarily telling you 3 sig figs. All right, we'll have this logic behind how many sig figs we choose, but just for the sake of practice, let's keep it at 3 sig figs for right now. Okay, so I'm going to put down a bunch of examples, and you're going to round these values to 3 sig figs. We'll keep it at 3. All right, so these are these 4 examples here. Everybody's going to take these and round them to 3 significant figures. Cool. All right, so this first one here, what's the value of my 3rd sig fig in this number? The 7, right? Because these leading zeros don't count. So if I'm starting to count, this is 1, 2. My 3rd sig fig is this 7 right here. And do I round it up or down? I'm going to round it up. So my final value here would be 0.0328. All right, put a box around it, final answer. All right, here, what's the value of my 3rd sig fig? Kind of gave it away, the 4. Okay, so does this round up or down? Down, so this would be 154, and this is where a lot of people stop and get it wrong, okay? Importantly, what is this number here? This is 1,543,225. If I told you I was going to give you $1,543,225, but I was going to round it to 3 sig figs, and I gave you 154 bucks, you'd be feeling pretty gypped, right? Went from a life-changing amount of money to like a nice pair of shoes, okay? So we can't change the number when we're rounding. We need to make sure that this 1 is still in the millions place, that this 5 is still in the 100,000s place. So I'm going to round this number, but I have to keep these placeholder zeros on the end here. So it's still 1,540,000. All right, so I don't change the value of that number. So we're not going to just chop off those digits when we round. We're going to make sure to keep that number the same. All right, this is another tricky one here. 2.5. I'm supposed to round this to 3 sig figs here. There aren't even 3 digits here, so I don't have to round anything. 2.5. What's wrong with that answer, though? There's only 2 sig figs. And what did I tell you? When you round to 3 sig figs, your answer has to display 3 sig figs. So how am I going to write 2.5 but with 3 significant figures? Add the 0 on the end. Awesome. 2.50 is how I would round that to those 3 significant figures. Okay. This is another kind of odd one here. 109.56. My third sig fig that I'm rounding to is that 9. Is that 9 going to round up or down? Up. So that 9 rounds up to a 10. So now I'm at 110. But again, can I stop there? No, because that number is, as displayed here, only has 2 sig figs. Okay? I need to have that 0 here represented as a significant digit. I can't just tack a 0.0 onto the end here, though, or now it has 4 sig figs, right? So what I'm going to do is something you would never see in a math class, but you'll see in a science class, is just the decimal at the end of the number with nothing after it. All right, if we think about our rules for sig figs, these trailing zeros, when do they count? If there's a decimal in the number, so we're just going to put a decimal in the number there to indicate that that last 0 is indeed significant. All right, so again, you would never see this in a math class, but we will see this in science. This represents 110 with 3 significant figures. Okay, so we learned how to count sig figs. Now we learned how to round to a specific number of sig figs. Okay, so this is going to be important because now we're going to start doing math with these measurements. And when we do math with these measurements, there's going to be this certain logic behind how many sig figs we display in our answer. Okay. So this is what we're going to call carrying sig figs. And we're going to have these rules for how many sig figs our answer should display when we do a math problem. Okay. Importantly, there's 2 different categories of operations that we're going to see in this class. We're going to have, mostly we're going to be doing a lot of multiplication and division. Or some addition, subtraction. And we're going to put these next to one another at the very top to remind ourselves that we are going to have different rules depending on what operation we're talking about. So multiplication is a different set of carrying rules than addition and subtraction. And we don't want to mix these up. Okay? We're going to do first multiplication division. These are the easier ones. All right, so let's lay out our rules for multiplication and division. Okay, what I'm going to do is I'm going to leave some room up top here for those rules, and I'm just going to put an example problem down here at the bottom. All right, let's say that we have 3.259 times 4.1. All right, step 1, do the math. All right, get your calculation done first. Apply your sig fig rules at the very end. Okay? in general, in these calculations that you do for this course, there's going to be points awarded for sig figs, but doing the calculation correctly is the most important part, right? The sig figs are like the extra little bit at the end there. So we're going to punch into our calculator 3.259 times 4.1. Y'all can trust me here, my calculator spits out 13.3619. Okay? So now we got to apply our sig fig rules. What we're going to do is we're going to count the number of sig figs in each of those inputs. All right, what do I mean by input? What's an example of one of my inputs here? The 4.1. What's my other input? The 3.259. This, my answer, is my output, what the calculator spits out, right? So I'm concerned with what my input sig figs are. So that 3.259 has how many sig figs? 4 sig figs. And what about 4.1? 2 sig figs. All right, so I'm going to compare these numbers. All right, whichever input has the fewer number of sig figs, all right, that's how many we're going to round our answer to. Okay? So I'm going to compare my 4 sig figs for my one input, my 2 for my other one. Which one of those two numbers is fewer? 2. So that means I'm going to round my answer here. This gets rounded to 2 sig figs. All right, and we just discussed our rules for rounding. So if I take this 13.3619 and I round it to 2 sig figs, all right, my final answer displayed with the correct number of sig figs is 13. Okay, what's up?
So there's only a 0 that's when we're at the decimal. There's no 0 and you don't have that.
Correct. This number already, you could, I mean, it wouldn't, like, that's fine. It's just because it's a non-zero digit, the 3 is already significant. Cool. All right, so that's all of our rules for multiplication division. Not too bad. We got to count the input, the sig figs on the input. Whichever one has the fewer number of sig figs, that's how many our answer should have. All right. So let's do a practice. Another. We'll do 2 more examples. I'll put these down for y'all to complete. Alright, so I'm going to punch this into my calculator. 4.6 divided by 0.03557, and I get 129.3224 and some change. Alright, what you'll do is you'll see me always carry a bunch of extra digits beyond the sig fig, but that's all I'm doing is kind of adding some extra digits on there, right? How many sig figs does 4.6 have? 2 sig figs. How many sig figs does 0.03557 have? 4, because we don't count those leading digits. So then how many should my answer have? 2. Okay? So importantly, when I round this to my 2 sig figs here, it doesn't round up or down? Round up. It doesn't become 13, but 130, right? Because I don't want to change the value of that number. Am I going to put a decimal at the end here? No, because I want to make sure my answer displays 2 sig figs. So if I put a decimal on the end, it would be 3. So no, I leave that decimal point off, and boom. All right, so 2.00 times 4.0. I don't trust myself, so I punch it into my calculator, and my calculator spits out 8. All right, I'm going to go back and I'm going to apply my sig fig rules. 2.00 has 3, 4.0 rather has 2. So then how many sig figs should my answer have? 2. So what am I going to do? Tack that 0.0 onto the end there. 8.0, boom. Cool. And again, remember, the amount of digits displayed, it tells you something about the precision of that measurement. So the bottom line is when we're multiplying 2 numbers together, we can't get an answer that's more precise than our inputs. No, we're limited on the precision of that answer based on what those inputs are. Whatever our least precise input is going to dictate how precise our answer is. All right? So, multiplication division rules, again, we have different rules for addition subtraction. So now we're going to lay out our rules for addition and subtraction. Okay? So similar to what we did before, I'm going to leave some room up top here to explain what these rules are, and I'm going to jump to kind of the middle of the page to put down an example. Our first example, let's do 8.2 plus 4.335. Okay, so just like before, step 1, let's go ahead and do the math. So I'm going to punch this into my calculator here. I get 12.535. All right, but now this is a different set of rules than multiplication and division. What we're going to see is it's not about counting the number of sig figs in our input. It's going to depend on where the position of those sig figs are. All right, and you can get kind of good at this after you do it a whole bunch and you can shortcut it. But for right now, we're going to make sure to do it the long way to make it really obvious what's going on here. So what we're going to do is we're going to rearrange where we stack each number at the decimal. All right, so what do I mean by that? I'm going to rearrange this math problem here to look a lot like what it looked like back in elementary school when you were first learning how to do addition problems, right? Remember when you were first learning how to do addition, we would stack them in such a way that the ones were in the ones column, and the tenths were in the tenths column, and the hundredths in the hundredths column, et cetera, et cetera. Right, so we're going to put that back in that old school format of stacking up our addition problem. And so now we have our answer here. Again, all my tens are in this tens column. My ones are in these ones column, tenths, et cetera, et cetera. All right, so everything's all lined up. Okay, now we're going to mark the last sig fig of each input. All right, so 8.2, what would be the last sig fig? That 2. All right, I'll use a different color. What would be the last sig fig in my 4.335? The 5. All right, and what we're going to see is, again, it's not about counting. It's about the position of these sig figs here. Okay, so last step here is whichever position is least precise, and by that we mean furthest to the left, is the position of the last sig fig in your answer. So, zooming in here, what do I mean by that? Again, I have these two positions marked. I have my tenths column marked in my first number, and I have this thousandth column marked in my second number. Which one of these is the least precise position? Which one of these sits further to the left, the red or the green? The red, which means that that will be the position of the sig fig, of the last sig fig in my answer. All right, so let's just kind of annotate. This one is the least precise because it is the furthest left. All right, so that becomes the position of the last sig fig in my answer. So if I round my answer here to the correct number of sig figs, my final answer here would be 12.5. Okay? And let's just note that if I had incorrectly applied my multiplication and division rules, I would have gotten the incorrect answer. Right? 8.2 only has 2 sig figs, and yet my answer has 3. Yeah, we can gain or lose sig figs when we're doing addition or subtraction because it's all about the position of those sig figs, not how many we have. All right? So we got 2 different sets of rules. If I'm going to boil these down to just one word that I'm going to keep in my mind to help me keep track of these 2 different rules, multiplication division is all about the count of how many sig figs we have, whereas addition subtraction is all about the position. All right, so again, just trying to boil these rules down into one word that's going to help me remember the difference. When I'm doing multiplication and division, I'm counting sig figs. When I'm doing addition subtraction, I'm paying attention to the position of that last sig fig. Bless you. All right, so let's just do some practice here, some addition subtraction practice. So step one, I'm going to do the math, punch this into my calculator. I get 4.225. All right, but now that I'm going to do my sig figs, I'm going to rearrange in such a way that I line everything up so that they're lined up at that decimal, so that all the ones are in the ones column, tenths in the tenths column, etc., etc. Boom. And now I'm going to mark the last sig fig in each one of these numbers. All right, 13.475, that 5 is my last sig fig. 9.25, again, that 5 is my last sig fig. All right, but my answer is going to be rounded to which one of these positions, blue or red? Blue, right? Whichever one is furthest to the left, my least precise here. So that means when I round my final answer here, it will be 4.23, right? I'll round up since it's a 5. Boom. All right. This next one's a little weird. And so what we're going to do is we're just going to blindly follow our sig fig rules, and then we'll take a step back and try to understand why we get such a weird, bizarre answer. All right. So first of all, if I punch this into my calculator will spit out 1500 and 1.63. Okay? But now I'm going to rearrange this. All right? I don't have a decimal explicitly represented in this number, but I know where it is. Okay, let's move this over. And now my answer, lining that up at our decimal. Boom. Okay. So what is the last sig fig in 1500? That 5. There's only 2 sig figs in this number here because there's no decimal point. So I don't get to count those trailing zeros. All right, 1.63, that 3 is my last sig fig. So then in my answer here, what am I going to round? To the red position or the blue position? To the red position. And so if I round this number to those 2 significant figures, my answer is 1500. All right, so what the heck? I just took 1500, I added 1.63, and you're telling me that the answer is 1500 here, okay? Well, I took this very imprecise number. My significant figure is all the way over here in the hundreds place, and I added some teeny tiny precise number to it. Well, this number that I started out with was already pretty squishy, so it's not going to change the value of that squishy number to add this very, very small quantity on there, all right? Maybe a sort of real world example would be my house is in Corsica, all right? So I live in Corsica, and I got some land and some chickens and some fun stuff like that, all right? But it is 39 miles that way, okay? So from right where I am, 39 miles in that direction, cool? If I take one giant step back, how far away is my house? 39 miles. This 3 feet that I just took a step back, this 0.003 miles is not going to make a difference because that 39 was already a squishy number. That 39 means it's somewhere between 38.9 and 39.1. Adding 0.0003 onto that is not going to change that, right? Again, it's not going to change my estimation because that first number was already pretty squishy to begin with, was not very precise to begin with. So that's what we're seeing here. That's what our sig fig rules are doing for us, making sure that we're not misrepresenting how precise our answer is given our inputs. If we have a real squishy input like 1500 and we add something teeny tiny onto it, we don't get to update that value. It's just going to stay 1500. Okay, so again, following our sig fig rules, but logically that's why we see the same answer here as what we started with. Okay, so measurements, it's been all about measurements, right? And we spent a lot of time talking about the precision of these measurements through these sig figs. All right, the other important component of all measurements are the units. Okay, so we're going to introduce you to these units that we use here in chemistry. All right, So every measurement that we have, we're not just going to have this naked number, there's also going to be some units on the end, and that tells you what it is that you're actually measuring. In science, we use what's called the metric system. All right, science and the rest of the freaking world uses what's called the metric system. Okay, America has very stubbornly held on to what's called the imperial system, where we use pounds and feet and all that jazz. Science and the rest of the world has changed to this other system of measurement, this other system of units. Okay, and it's going to depend the unit that we're going to use. All right, actually, let's call this our metric system. These are what we call our base units. We're going to use a different unit depending on what it is that we measure, right? So if I was going to measure my height, I would do so in feet and inches, but if I was going to measure my weight, I would do so in pounds, right? So we have these different units that we use depending on what quantity it is that we're talking about. Same thing in the metric system. So the metric system, if we're talking about mass, we use the units of grams. All right, we can, I guess, header our table here. This is our quantity. This is our units, and we're also going to put in the abbreviation. For grams, we abbreviate that with lowercase g. Okay? If we were instead measure, so first of all, what is mass? All right. Strictly speaking, mass and weight are not equivalent to one another. Your mass is consistent here on Earth. Your mass is consistent anywhere in the universe, so your mass is the same here on Earth as it is on the moon. Your weight is your mass plus the force of gravity factored in there. Okay? However, we're doing chemistry here on Earth. We're not doing chemistry on the moon. So a great way to think about mass is really analogous to weight, right? It's a measure of how heavy or how light something is. That's what the mass is. Okay, so for mass, we use units of grams. We have that lowercase g. We also will measure volume. What's volume? So volume is used in units of liters, but like, what is the concept of volume? Volume is how much space something is occupying. All right, so we can talk about the volume of this room, how big this room is, for example. All right, in the metric system, we use units of liters, and we abbreviate that with an uppercase L. All right, we could also measure length or distance. Okay, and in the metric system, our base unit is the meter. And we have a lowercase m for meter. All right, we will also measure time, often in chemistry. All right, how long a chemical reaction occurs for. The base unit is seconds. Now we could scale that up to minutes or hours depending on how long it is, but our base unit here is seconds, and our abbreviation is a lowercase s. All right, and then lastly, temperature. The SI unit, are, kind of the basic scientific unit, is what's called the Kelvin, has an uppercase K. We'll actually be using two different units for temperature quite often. We'll use Celsius a lot as well. We never use Fahrenheit, which is what we use in America, but we do use Celsius quite often. It turns out that there's something fundamental about this unit Kelvin, and I'm going to kind of punt on discussing what that is until we talk about our gases chapter. But nonetheless, there's a reason why Kelvin is considered to be our special base unit for temperature here. All right? Although we will typically use, or commonly use Celsius as well. We use them both. Okay, so depending on what it is that we're measuring in our or in our metric system, we have these different units. We use grams for mass, liters for volume, meters for distance, and seconds for time. And importantly, we have these abbreviations. The case does matter, all right? So lowercase g for grams, uppercase L for liters, lowercase m and lowercase s for meters and seconds. And the Kelvin, and again, we'll kind of punt on this until we get to the chapter that discusses temperature, but Kelvin is uppercase K. Okay? So what makes the metric system special or different is here in America, our imperial system, if we want to do really short distances, for example, if I wanted to tell you how big my iPhone was, I would measure that in inches. Okay? If we're going to go slightly larger distance, slightly larger length, like how tall I am, we would measure that in feet. And then if we're going really far distances, like how far away my house is, we would do so in miles. Right? So we have these different units depending on how the scale of what it is that we're measuring. They have the same thing in the metric system, but they don't actually change that base unit. They're still going to be talking in terms of meters. What they're going to do is stick a prefix on the front of it. So if they're talking about something small, they'll talk about it in centimeters, right? They'll put this centi prefix on the front. If they're talking about something very far away, they'll put a kilo prefix on there. So kilometers, kilometers, all right? So they keep the same base unit, and they just tack on these different prefixes, all right? So I want to introduce y'all to our constants page for this chapter. Let me get rid of all this real quick. We'll graduate to that. All right, so this big ugly page here is our constants page. All right, and our goal for the rest of the week is going to be to pick apart what this constants page is telling us. It's big and ugly, but it's really not too bad. But really what we're going to focus on right now is this table here. These are our metric prefixes here. Some of them I think you've heard of before, like again, centi and kilo, but there's a bunch of them. We can talk about something super teeny tiny in nano or pico, or something really large, tera or giga, all right? So these are all these different metric prefixes, okay? So let's just kind of see why they might be convenient to use. I'm going to make some room here, get rid of all this. Okay, so let's say that I had 1.2 times 10 to the negative 3 meters. That's how the length of something that I'm measuring. 1.2 times 10 to the negative 3. All right, so this would be a distance or a length measurement. And we could use this number in scientific notation, but generally speaking, we'd rather not. We'd rather scale our units to be matching whatever it is that we're talking about. Just like I could talk about the length of my iPhone in miles, but that would be ridiculously cumbersome, right? It'd be a stupidly small number of miles. So we like to use our units in scale with what it is that we're measuring. So what I could do here is this 1.2 times 10 to the negative 3 meters. What I want to notice is that 10 to the negative 3 is this milli prefix. And so it turns out that 1.2 times 10 to the negative 3 meters is the same thing as 1.2 millimeters, where I've substituted out that 10 to the negative 3 for that milli prefix. Okay, and now I got a nice convenient number to work with, not a number in scientific notation. Okay, let's do one more and then we'll pick up with this next time. Let's say that we had 4.65 times 10 to the 6 liters. Some absurdly large volume. All right, I got an Olympic swimming pool here. All right, well, 4.65 times 10 to the 6 liters, 10 to the 6, kind of cumbersome to work with. So what prefix could I replace this with? If I look, 10 to the 6, that's this mega prefix, using that uppercase M. So this measurement here would be equivalent to 4.65 mega liters. Okay? All right, where again I replace that 10 to the 6 with that mega prefix. Cool. So that's all well and good when it's really spelled out for us in scientific notation. But we want to be able to do these unit conversions more generally, or prefix conversions more generally. And so that's where we'll pick up with next time. How do we do these, use this table here to do any prefix conversion?